Let's finish up the worksheet with number 11. It's asking us to complete the following table. Now for metals and ionic compounds, I want to describe the components. I want to describe the overall charge, yada, yada, yada. So for each of these two things, I'm going to describe what it's asking for on the left. Now, ionic compounds, their components, okay, what they're made up of individual ions. Makes sense, right? They're ionic compounds. Metals, in order to make a metallic bond, all you have to have are a bunch of metal atoms. Okay, metal atoms. Just give me some chromium, some iron, some nickel, some copper, some zinc. Just throw them together in just a pure metallic sample, and you're going to have a metallic bond. Okay, you're going to have a metallic bond. And you might be thinking, yeah, but within that metal sample, you're having positively charged cations, aren't you? Yeah, you are, but you're not inserting metallic ions. The metals will ionize on their own within the sample. You're just throwing metal atoms in there to start with. Overall charge, well, these bad boys, these metals, yeah, they got positively charged cations, but you're also not losing those electrons. It's not like they just disappear into the ether. So you are actually remaining a neutral here. And like we learned about ionic compounds, is that when you have a +2 charge over here, there has to be a total of -2 charge over here. So if you have something like a chloride ion that's only going to form a -1, you better have 2 of them, so that the magnitude of these 2 charges equal out. And when they equal out, you also have a neutral compound. Conductivity in the solid state. Metals, yes. Okay, or check mark or whatever. In the solid state, ionic compounds do not conduct. Remember, conductivity has to do with the ability to have charges move. Okay, and when you're a solid ionic compound, you're stuck in a lattice structure. You're stuck in a crystal. You can't move. Okay, so in the solid state, no. Melting point for metals can actually be anywhere from low to high. You might think, oh, but in the notes you said that gold has a very high melting point. It does, okay, but here I'm not talking about just gold, all metals. Mercury, for example, is a metal, and it is liquid at room temperature. That's a pretty low melting point. Okay, so anywhere from low to high, quite a bit of variety there. But ionic compounds, boom, they are always high, always. Malleability. Oh, no, I skipped hardness. Sorry. Metals. How hard are they? Well, yeah, you got some hard metals, right? You have some hard metals, but you also have some soft metals. For example, gold, in the olden days when you'd have a pure gold coin, you gave it to someone and they wanted to see if it was real or they were just they were being fooled, what would they do? They would bite it, because if it was pure gold, like the person claimed it would be, the metal would give a little bit. You could actually reshape gold, pure gold, with just your teeth. You can bite into it and it would move because it's soft. Right? So metals will vary from soft to hard, even though a lot of them, in our experience, what today in the industry we use metals for, they tend to be hard. Hardness of ionic compounds. These are stuck in huge crystals, so these are always very hard. Very hard. They tend to be brittle, but hard. Okay, now on to malleability. Do metals have malleability? Yes, they do. They're toting that sea of electrons model. Are ionic compounds malleable? No, they are not. They are very brittle. Okay, if you add enough force in one direction, they will shatter. And in the same way, metals, are they ductile? Yes, they are, all because of that sea of electrons model. Ionic compounds, no, you are not going to be able to reshape those into wires. Not going to be able to change the three-dimensional shape of that crystal at all without it breaking. Okay.